Okay. Hi, everyone. Welcome to our RefoundEd Summit final session for Thursday. We are so excited to have Gillian, who's going to be diving into the counting principles. Thank you so much for being here.
Thank you. I am so excited to talk all things math and building early number fluency for kids on a Thursday night at 8 o'clock. So I'm just going to share my screen with everyone here so that you can see, and we will get started. So the last session we had, I have two sessions, and one of them we talked more about later addition and multiplication. Tonight, we are talking about the counting principles. This is pre-K or early primary that we're talking about here, and really laying the foundation and building number fluency. Because a lot of the times when we think about counting or we're introducing numbers, we're showing them the number and saying, what number is that? And a child says it's number one, but it really just looks like a line to them and they don't really understand the meaning of what one is. Or we're looking for kids how high they can count. Oh, my kid can count to 50, but for me, in a sense, it's not so much how high a child can count, because that's really just memorizing things. My son, he loves trucks. And if he saw 10 different types of trucks, he can memorize those 10 different types of trucks, just like you can memorize a number and a numeral. But what does that actually mean? I'm more interested what children can do with those numbers. So say a child can count to 100, another child can count to 10 or 20, but they can manipulate those numbers and they actually have understanding of what those numbers are. That is much more powerful than the child that can count to 100 and really doesn't understand magnitude of number. And we're going to really dive into this because I see this happening a lot. More doesn't mean better. Counting faster to 100 doesn't mean better as well. So I'm going to dive deep into the nitty gritty of what the counting principles are. So on tonight's agenda, we're going to start off by talking about the why the understanding over the memorization is so important. Then we're going to go into the 10 counting principles. What are they and how to implement them? And then third, we're going to be starting talking about addition and subtraction, because that's really the early number sense that's happening with our children. We really want them to have flexibility and fluency with that, because if we don't lay this foundation, we see gaps later on. I've had experience in even later primary and junior and even intermediate, where some of these foundations haven't been fully met yet. And the gap has just gotten larger and larger because we haven't addressed those things. And we're just trying to get kids, well, just memorize that fact and you'll be okay. Well, not really, because when we get to larger magnitudes of numbers, if they don't have that foundation or those strategies, then it actually creates a barrier of it. So we really want to have the understanding prior to the memorization. And I have to disclose, this doesn't mean that I don't think kids should be knowing their facts. Knowing their facts is incredibly, incredibly important. But there's a difference between memorizing and between memorization and automaticity. So automaticity means that something is retrieved from your brain quickly because there's understanding that's involved there. It's now automatic. I haven't just memorized something and I don't really know what it is, but I know what I can regurgitate information, but it becomes automatic because I've done it so many times and I'm just incredibly flexible with it. So those are the three things we're going to be talking about today. And this is you feeling confident, being able to implement all of these things through your children and your lives. While I will be saying some different examples of how you could implement this. Again, the answer is always, it depends. It depends what your child is interested in. It depends on your environment. It depends on the materials that you have in your playroom, what your child plays with. The answer is always depends. So tonight, we're also going to be really talking about like the content, the definitions of what these things are. It can seem like a lot of information, but there will be a kind of PDF little cheat sheet to go with you that you can keep, because there are 10 of them, and that you can reference as well. And just a little bit about me. So I've been in education for the past almost 15 years now. I've taught French immersion in the elementary grades. I really align with project-based, inquiry-based type of learning. And I also have experience as a math coach as well. And I'm very, very interested in how the brains of children learn and the process of that learning. And now I currently work with kind of alternative education, more nature-rooted schools, on how to seamlessly weave math through authentic experiences, homesteading, entrepreneurship, baking, cooking, gardening, all the skills you want your children to know, practical life skills. So I really work with them on building math programs based on their environment, because it will look different learning math on a farm as it into more, the different kinds of environments that you're in. So that's what I really do. I consult with them. And then I also run professional development for their teachers as well, so that they have an understanding of the essential understandings of mathematics so that they can seamlessly weave it through for those children. And this is just to give you a little snippet of what I align with and what my experience is. So I was in the classroom for a really long time. And again, these are pictures from my classroom. Not the best quality because from a while ago too. But as you can see, sewing, I had girls here creating their own scrunchies and building a business around it. Woodworking was a large part of it. Kids love building. There's so much math involved. Baking, cooking, again, there's math and number sense everywhere. And really integrating nature as well, getting outside, building gardens, and also a lot of engineering involved. If we're going to learn about gears, let's take the bike apart and put it back together and figure out how it works. So really that innovation, hands-on experience for all the kids. And what I found was that there's numbers everywhere, even when you're reading books. So we can do all of these activities through experiences, but we want to make sure that what are we doing when those numbers come up? Are we just reverting back to teaching them kind of very procedural thinking or rote memorization when those numbers come up? Because it's great that they get this experience, but let's also teach them how to strategize and understand math as well. So that's the piece I'm going to be focusing on tonight. Not so much these experiences, but what you do with those numbers when these situations arrive. And then just a disclaimer that I did not make up these counting principles. They are not mine. I'll be referencing people, and the PDF that you get will be the mathematicians that have done the research, and this is based on evidence. And I have implemented all of these too. So I've seen the benefits and the outcomes when you do this and really lay this foundation. So we are going to get started here. And I'm just going to do a quick, what's the same and what's different. So on the right-hand side, we have a 6 plus an 8, kind of like on a flashcard. And then on the left-hand side, we have a number line and 10 frames there. So I'll just talk about how the right-hand side, the stacking of the numbers, again, it's very abstract. It doesn't really tell me much. A lot of kids just see 8 as 2 circles on top of each other. They're like, I see a circle and another circle. What does that actually mean? What does the magnitude of that number mean? On the left-hand side, you can see the 10 frames. So I can see that 8 is more than 6. I can see that I can take these dots and move them over and put this in this 10 frame here. On the number line is a really powerful visual model that we use from kinder all the way up. You can use it with fractions and decimals later on as well. And we really want to build this linear number line in kids' minds where they can move seamlessly up and down the number line. So the standard algorithm, which is on the right-hand side of numbers stacked on top of each other, it doesn't tell me much about the strategy that I'm using to find the answer. On the number line on the left-hand side, you can see that this person started at 6 and added 4 to get to 10, which would be a friendly number, which is a really great strategy, and then added the rest of the number. So again, we want to be using powerful visuals and models. That's something I am very, that I think is critical that kids need, is the visual, because the right-hand side is very abstract. And I have so many people tell me that they're not good at math. And I always tell them it's because they had a bad experience with math. They probably learned very abstract concepts too quickly without the concrete, the physical touching, manipulatives, and experiencing, then the visual phase, and then the abstract. So I'm going to show you how we weave that through the counting principles. So here they are. I don't expect anyone to memorize all of these. We're going to go through each one. And like I said, you'll have a little cheat sheet at the end that you can reference. And I actually, on the cheat sheet, I have little question prompts that you can ask your child as well to help you out. So that'll be really, really helpful on hand. Again, I've been using these for the past 10 years. So they're kind of at the back of my head now, and I don't expect anyone to do that. because I research them for fun, just because that's what I'm passionate about. But I know no one else has time for that. So this is the progression. We want to make sure that we're not just showing kids numerals right away. The numeral is the 6 here. I mean, you can, but if they memorize it, again, it's a line and I see a circle, it doesn't mean much. So we really want to hang out in the concrete phase here, physical things that you're touching and counting. Then we move to the visual models. And I talk about visual models, circles representing something. So say you're counting bears or little dinosaur toys or something. You don't want to be drawing out the whole dinosaur and creating a visual for it. You want to take a representation, so an X or a circle or something quick that you can do to represent that, so that the child sees, okay, this dinosaur represents this circle. And so I have 6 dinosaurs, 6 circles, and then this is the number 6, the numeral 6. So that actually comes last. So spending a lot of time earlier in the concrete and visual phase. I find we fast forward really quickly to the abstract phase. So the first counting principle is one-to-one correspondence. And you might notice that you do a lot of these already, but there's just a few things to iron out. So this is counting one item at a time and saying the word as you count them. Some children will count the same object twice, or take their finger and touch different objects different times. You want them to touch and tag it and name the unit. So 1 train, 2 trains, 3 trains. The reason why I always just reinforce naming the unit is because it gets them in the habit of later on, when I'm talking about centimeters or meters, those are 2 very different things. And if I'm naming 1 train or 1 banana, 2 very different things, right? So even if they don't name each one, just at the end though, oh, that was 6 what? Were those 6 dinosaurs? No, those are 6 trains. Oh, okay, those are 6 trains. So just making sure they name that unit, and it helps later on, because I find a lot of children will say when they're measuring something, they won't name the unit or they'll mix up the unit, and that can totally change what you're doing. Even when you're baking grams, kilograms, we want to be naming that unit. And they have to understand that what gets counted is separate from what's been counted. So sometimes kids will count and they'll recount stuff that they've already counted. They don't understand that that's done. And this is the rest that I'm counting here. So just keep in mind that. And then comparing collections of things. If I count 6 trains on this side and I count 5 trains on this, or 5 cars on this side, comparing them. Which one has fewer? That's a word that you want to introduce. Which one has fewer? Which one has more? What is the difference between the 2? So the difference meaning not the trains are blue and the cars are red, but the difference being how many more in one of them. So the trains have 1 more. So just comparing collections of items is also another thing that you can do for that. The next one is stable order. So this is the sequence of counting. Again, one's pretty obvious as well. There are different ways to count, but there's an order. It has to be very, very specific. 4 will always come before 5. 3 is always becomes before 4. So this is a number path. I've talked about number lines a lot, but something you can use before that is just a number path. And again, this is something that you can just print off. They're just squares and it's 1 to 10 here, but they just use their finger and they can see the sequence and the stable order of what's happening here. With stable order, if a child misses or skips a number, and you notice that a lot. My son's doing that right now. He'll count to like 8 and then say 11 sometimes. He'll just skip them. So what I do is I say to him, okay, I'm going to count. I'm going to skip a number and you have to guess which number I forgot. Okay. So they have to listen and kind of think about what number you're going to miss. Another thing that you could do is not tell them. But my son the other day, he said, Mommy, you have to take 10 hockey shots. So I said, okay. So I said 1, 2, 6, 7. And I just started miscounting. And he kind of looked at me like, wait, what? What? And I was like, what? He couldn't really explain it yet. My son's really young, but them starting correcting you. Instead of you always correcting them, have them try and correct you. And when you make mistakes, you're like, oh, I made another mistake. So making mistakes on purpose and having them correct you is just something that you could do too. And counting backwards. Sometimes we kind of forget that and leave that on the back burner, but counting backwards is something really important. So if you count a collections of items, you can ask them, okay, we have 18 items. If we count backwards now, will I land on the same numbers that we did when we counted forwards? Like, will we say the same numbers out loud? I'm like, I don't know, let's see. So then you count backwards together and then starting at a random number and ending at another number. So, okay, this muffin tin has 6. We already know there's 6 in this one. Let's start at the number 6 and then count to the number 18. Some kids will have to start back at 1, and some kids will be able to just start at 6 and go. So that's something to recognize as well with stable order. An interactive number path is also a good idea. So if you have, again, a number path is literally just number 1, 2, 3, 4. There's no 0 there for a reason. On a number line, there will be a 0. On a number path, there's not. So on a number path, kids can put their finger on the number 1 and they can kind of move it along. I can add 1. On a number line, like we saw earlier, I'm just going to bring this up here, that on a number line, kids get confused sometimes because they'll start counting these ticks here. Do you see that? They'll start and they'll count 1, 2, 3, and they kind of get messed up with that because they're not counting the spaces between the numbers. They're counting the little ticks on the number line. So just before you introduce the number line, I highly recommend doing a number path first and then moving to the number line. With the number path, what I'm doing with even my son right now is we have one, just little pieces, or you can put magnetic on your fridge. And I have some missing. So I put 1 on one end and 10 on the other end, and I fill it in and I leave some missing. And he looks at it and he has to guess which number is missing. So that's kind of getting into spatial reasoning as to looking which number that could be that's missing there. So using missing numbers to complete the stable order. And then another option too is to get a rope or a string or something and attach it to 2 ends of something. So it doesn't have to be far. It can be really far. I've done it, in classrooms before where it's one wall to the other wall and they have 10 numbers and they take them and they have to try and place them on. Not in order though. I don't start with 1 and then 2. I give them the number 6 first. And then you can have a clothespin and they start clothespinning them on. So it's really a physical experience in embodying, okay, between this wall and this wall, where's 5? Like, where's the middle? Like, do they know what half is? Half is so, so important. So starting with half, or if you gave them the number 6 first, talk about where you would go. Oh, well, I found half and it's a little bit more than half. So I found half first and I went a little bit more. Or if you got the number 4, I found half and I went a little bit less. So that interactive number line and being able to place numbers between a space is so incredibly important. I highly, highly recommend doing that. And it doesn't have to be a large space. You could literally just do it on your kitchen table, right? Between the end of your kitchen table and the other end, and start with the number 6 though. I have 1 in 10, or you can do 1 in 20. You could do 1 in 50. You can really choose the magnitude of number based on what your child ability is. So if I have one end, 1 to 10, and on the other side of the table, I have 1 to 50, where would the number 7 go on each side? Like it will look very different. So that's working on spatial reasoning, which is something that's actually very under-taught. And a lot of research shows that high spatial reasoning skills at a young age means later on success in mathematics, higher achievement later on. So spatial reasoning is anything, even with your body movement, like even with kind of sports or playing on a playground. It's mental rotations in your brain that you can do, closing your eyes and being able to visualize what's actually happening. So taking those numbers and being in that space. So I was talking, I was at a conference and I was talking to someone. If you have the numbers 1 to 10, and think of a child who doesn't really understand those magnitude of numbers. Imagine we had on a number line 1 to a trillion. Okay. Numbers 1 to a trillion. And you were given the number 1 billion. Like, where would you go on the number line? Right? You would be like, okay, well, here's 0 and here's a trillion. Where would 1 billion be? right? Well, like we'd probably go to half first. What's half of a trillion? You're like, how many billion is half of a trillion? Magnitude, and like you're starting to think about that. And you're like, okay, well, a billion is probably actually really close to the one when I think about it. And that's what you have to think about kids' minds. While 1 to 10 seems so simple to us, that's actually what's happening in their head. And being able to spatially, strategically figure out where numbers are in that stable order, in that number line. And again, for higher grades, I've done this with fractions and decimals as well. I could have 0 and 1 and give the fraction, 5/6 or, something like that. And they have to figure out where it is on a number line. So again, it's a very powerful visual and model with longevity, and you can use it concretely, again, by string and clothespins and cue cards with a number on it, or you can use it visually as well. So that's what the interactive number line. I love number lines and interactive ones where kids are placing them on, if you haven't noticed. Another thing that you can do too, talking about magnitude of numbers and spatial reasoning, is estimation. A lot of the times I'm even starting to ask my son, how many do you think are there? And I'm just asking again, not forcing. And sometimes it doesn't happen. He looks at me, he's like, just walks away and wants to go play trucks. And that's totally fine. But when he's into it, I want to talk about and listen to his thinking. So even in this bowl of oranges or bag of oranges, when we go grocery shopping, like how many oranges do you think are in here? What would be an estimation too high? What would be an estimation too low? And what would be a reasonable estimation? So estimation is another concept that's really under taught as well and is extremely important. Kids understanding what a kilometer is, like being able to estimate that and physically experience that, or even looking at objects. And if I look at these oranges, I have to consider that there's some underneath here. Like I have to kind of look at it, pretend I'm in the bowl and like looking at it from the other end, and how many are behind there. It's not just the ones I count. So teaching them what estimation is and then talking about their strategy to figure out that estimation. They didn't randomly choose it, right? Maybe they counted the ones they saw and they doubled it because there's some underneath. So using that type of language to describe what they see. I've also make, blender muffins, blender pancakes, because a few ingredients and the blender is the best way to go. And I have it filled up and I ask, how many pancakes do you think we can make with this? Like, what do you think? And just being able to listen to that can be really, really interesting. And then talking, well, it depends on the size. Are we making little pancakes? Are we making big pancakes? Whenever we make cookies or little energy balls, before I roll them out, we look at the dough and we think about, okay, how many do you think we can make? So they kind of have to and they're looking at it and they're thinking about it and they can tell you an estimation. And then sometimes I would ask, well, what if we changed the size of the energy ball that was this big to the size of a tennis ball? How would our estimation change? So maybe it would be, if we thought it was 10 little small ones and now we have a big one, oh, well, maybe I'm going to divide my answer because it's double the size. So really just using that language and thinking about the process of thinking. This is all done through conversation with children as well, which is so important. We need to talk to them and listen to their process of thinking. And then as adults, to model thinking as well, model efficient thinking and model efficient strategies. The next counting principle is order or relevance. So this means that the order in which items counted is irrelevant. The ordinal system matters. So if I have something first, second, and third, that has to be I have to count those in order. But the cardinal system doesn't. I can start at any point and still count, and it'll still be the same amount of items. So for example, these little rocks here, I had someone counting them that we collected on a nature walk. And they said, what if we started counting up here or over here or at the bottom? What if we started counting on the left or the right? Will we have the same amount of rocks? And a lot of kids will look at you and kind of like, I'm not sure. I have to recount them, I don't know. And then if we move them in a line, I didn't add any or taken any away, but can you predict how many there would be if we started on the right-hand side? And they'll count them. And I said, can you predict how many there would be if I start on the left-hand side? And if they have to count them, that means they don't really understand this concept yet, that I didn't take any away. We're just starting at a different point. Again, a lot of these things might seem very natural to us. We're like, of course. But to a child who's learning about numbers, it's actually very complex when you think about it. Another thing this is my son, he was peeling carrots and he counted them out. And then I said, well, what if we started counting over here? He had to count them out every single time. Like he did not believe that the number stayed the same, even though he had peeled them and counted them. So that's just something to consider that, again, my son's not there yet. He's about 3 years old. And I always tell people, I'm like, we're not in any rush by any means, but I just find it so fascinating, kids' brains and listening to where they're thinking. And when we know this information of what the counting principles are, we're able to make those moves to kind of push their thinking. Order of relevance is incredibly important as well because it brings in the concept of commutative property. And commutative property means that 3 plus 4 is 4 plus 3. So I can add numbers. It doesn't matter the order in which I add the numbers, the sum, the answer will still be the same. So I could add the oranges first and then the apples, or the apples first and then the oranges, and it'll still be the same. And I've actually seen later on kids not understand this concept, and it's because it's one of the counting principles that they really don't have solidified yet, that it doesn't matter which way I add numbers. And that goes for multiplication as well. It doesn't matter which way I multiply numbers, I will get the same product. And you have to think about what would be the most efficient way to add these numbers. Should I switch them around? Because I have the example here, 3 plus 9. And when a lot of kids see 3 plus 9, they'll start at 3 and go 4, 5, 6, 7, and they'll count out 9, not knowing that this is, and that's very normal to start, but we want them to know that, well, why don't we just start at the 9 and add 3 more? And they're like, wait, can you do that? Can you switch those numbers around? What are you talking about? And I am always talking about efficiency, least amount of steps, least amount of brain power so that we can put that energy to something else. We want the least amount of cognitive load for our kids so that they can excel, they can problem solve in other areas. We want them to be really flexible with numbers. So this is why this is the beginning of that, of adding numbers, and why this order or relevance is really important to think about. Cardinality is the next counting principle. And this is understanding that the last number they counted is the quantity that it represents. So my son still does this. So if we count out the muffins and I put them so we counted out, whatever, there's 12 of them. I put them in the oven and I say, how many muffins was that? He has to go turn the light on and recount them because he doesn't understand that 12, that last number means the whole quantity. They just think it's another number. It's not any different than the other ones before that, right? So that's something. And I was telling my husband about this. He's like, I didn't even know that was a thing. But when he saw it with my son, he's like, oh, I see that. He keeps having to recount. And after a few times, he's like, okay, it's 12. It's 12. But right away, they should know that. Even when you're cleaning up toys and you put them in a bin and you close it and you say, oh, how many toys did we just clean up? And if they have to recount the amount of whatever blocks you were cleaning up. I've done this at the grocery store with my child too, where we're getting pears and we're putting them in the bag and we count 7. And then I go, okay, well, how many pears did we get? And he doesn't know because he has to kind of go in and recount them. Again, not knowing the last number represents quantity. So that's something just to consider as well. Conservation. So this is understanding that the count of a set of group of objects stays the same, no matter if they are spread apart or close together. A lot of kids assume that when things are spread apart, that there are more, and that when things are close together, that there are less. So again, some of these things like this one, it's just something to talk to your child about, and it's something that you can overcome pretty quickly, some of them, but them just understanding that just because things are spread apart, even though it's the same quantity and together, it's really the same thing. It's the concept of conservation. Abstraction requires an understanding that we can count any collection of objects, whether they are tangible or not, and larger items are not worth more. So in this situation in the garden, I have 7 cherry tomatoes, 7 regular tomatoes, and then I have 7 vegetables. It's still the quantity of 7. Now, this can be kind of confusing for a kid because they'll think, well, the vegetable is bigger, so I get more, right? But it's still the quantity of 7. If I have 7 elephants and 7 mice, it's still 7. I don't have more elephants than mice. Cars, even my little guy's toy cars or cars in an actual parking lot, If I have 2 toy cars and 2 actual cars in the parking lot, it's still 2, right? So that concept can be a little bit tricky as well, deceiving for kids at the start. And counting non-tangible items, so such as sounds, actions, words, or steps. So we're always counting things everywhere. If you're playing on the drums, when you're playing catch back and forth, the words in a sentence, when you're walking somewhere, especially orientation. If you can describe location by the amount of steps from one place to another, even in your yard, right? Or from, even at my house, from my backyard to the fire pit, like how many steps is that away? Because a child doesn't, probably not describing it as how many meters or feet away, but they can count steps. So doing that is something that you can do too, to describe orientation with kids, is counting the number of steps from one place to another. Listening to birds chirp, if we're listening to something, oh, how many times was that? Can they keep track in your head of that? Clapping is another one. So just things that you can't see, non-tangible things that they can still count. And then after that, if they count something, say you heard a bird chirp and it was whatever, 6 times, I would say something like, oh, what does 6 look like with your hands? Show me with your fingers. Getting them to show you the number with their fingers is really important. My little guy's he's still kind of awkward when he's doing a 3. It's kind of hard for him to get his little fingers up there, but we want them showing you with your hands and saying, you showed me 6 like this. Is there another way to show 6? Oh, 6 we always show 6 like this all the time. 6 can also be this, and 6 can also be this, right? So showing them different ways of what 6 is, not always, this is also 2. So just keeping that in mind. And then I would go to the numeral. I would say, okay, this is how you do the number 2. This is it. That represents 2 things like that. So making sure that you get the numeral in there and them an opportunity to write it as well, but just talking a lot about the number and the quantity before that. So moving into the next one is called movement of magnitude. So understanding that as you move up the counting sequence forwards, it increases, and as you move down backwards, it decreases. It's very different from the alphabet where we go A to Z and nothing changes. It's just a letter. They make different sounds, but it's just a letter, really, right? But if we go 1 to 26, whoa, like one elephant and 26 elephants, that's very, very different, right? Or if I have 1 cookie and I eat 26 cookies, that's also very different. So the magnitude changes, and them understanding what magnitude is. And that's when estimation comes back in. Them really understanding number is important, especially with the unit attached to it, because 26 grams of something and 26 kilograms, extremely different. It was visually looks different. I don't think we spend enough time doing visualization actually of what things look like in our head as well. So doing a lot of that visualization of magnitudes of numbers is something that you can do. Also on the right-hand side, you can see having the same item and showing, with number 1 is 1, and you can see how it gets more as the sequence goes on is really important. Something else that I would do, questions that you always ask with magnitude, is what would be 1 more and what would be 1 less? What would be 2 more and 2 less? And this kind of gets tricky usually at the number 9. If you ask them 2 more, they're like, well, 10 and what's after that, or knowing what's before. For this, I actually would use a number line or a number path to start off. No, not that one. I would use this one here. This is kind of what I'm doing with my son right now, is that if he sees, say he saw 6 of something, I would say, what is 2 more? And I have him put his finger on it, and he slides it over once and slides it over twice, and he can see 8. What would be 2 less? Start at that number, put your finger on it, and go back, and 2 less. That would be a very abstract way to do it. And I would also do it with 10 frames. 10 frames are really, really powerful visual. I have a magnetic. You can get these off Amazon. They're pretty cheap. They are magnetic and they go on your fridge, and they come with these little circle dots of different colors. So they can add 1 more or add 2 more, and they can visually see how many that is. You can also do which number is greater, 4 or 6, and how do you know? So have them explain, well, how do you know 6 is greater than 4? Like, how could you describe that to me? Well, it's 2 more actually, because 1 more is 5 and 2 more, it's 2 more things. So then asking a question like that, you could do as well. With movement of magnitude, something I like doing is a concrete bar graph. So in this situation, even with my child right now, it's spring. So we're going to be spotting things on our nature walks. So you could choose different animals. For this, I just randomly chose some, a deer, a coyote, squirrels, and birds. And every time you go on a nature walk, count how many, or take a little clipboard and tally how many you see. And when you come back, add little snap cubes on. I love snap cubes or little cubes that somehow connect. They can really see magnitude. I can clearly see here that we saw more birds than deer. And after the month of April is over, so for my child, we just have the block set out. And if my child was a little bit older, he's not though, I would say, if someone saw these blocks, how would they know what it represents? Like, you and I know that this represents, we go on our nature walks and we see these animals and then we add a block each time. How would someone who didn't know, like, what if grandma and grandpa came in and they saw these? How would they know what this information represents? So you can make a title for it. It's the animals spotted in the month of April. These are the types of animals. Let's draw it or put a little sticker to represent it. So that when people come and they can see what this information represents. This is the beginning of data as well, collecting data. And at the end, you can analyze the data and draw conclusions from it. Okay, well, there's a lot more birds than deer. How many more? What would be 2 more? What would be 2 less? 1 more, 1 less? Those types of questions. What is the difference between the number of squirrels that the number of birds? So they can line them up and they can really see magnitude, and then them putting the numeral on it at the end. So them drawing out the number, connecting to the magnitude. So I can see 6 is more than 4. And I'm drawing the number at the same time and really talking about that. It's actually 2 more than 4. It's 2 more cubes than 4. So a concrete bar graph is something I highly, highly recommend doing. You don't have to do it for nature walks. You can literally do it for anything that you are keeping track of in your day-to-day experiences as well. The next one is, I'm just going to stop. Are there any questions? Oh, your kids would love that. Awesome. Yes. This is a really great one to do. And are there any questions so far? I know I'm flying through a lot of information.
It's perfect though. It's fantastic.
Yeah. Okay. If you have any questions too, just feel free to come off the mic too, but I'll stop at the end and we can ask more questions and we'll look at the chat. Just for time's sake, I'm just going to keep going here because there's a few more and I want to get through it all. So for subitizing is the next one. So subitizing is to be able to see and visualize a small amount of objects without having to count them. So I can look at something and I can see that when I looked in the sky, there were 3 birds. I didn't have to go 1, 2, 3. My brain just naturally put it together and I can see 3 together. This is very intuitive in us. Like, we are innately born with this being able to subitize. Obviously, children can subitize less than adults. But even if I have, 4 muffins out on the counter, can a child say, oh, how many are there? Do they have to count them by ones, or can they just see? Dice is a huge one. I highly recommend using dice any chance that you can get. And you'll notice slowly, it's interesting watching the process of which numbers they recognize on a dice and which ones they still need to count in the process of that. So when they're able to do 5 and under without counting, that's called perceptual subitizing. So again, that's 5 and under. Go to the next slide. And then conceptual subitizing is when there are more than 5 items. Okay, so that's kind of hard. You can't do, 7 items if they're all over the place. Even as adults, we'll kind of chunk them together here. So if we looked in the sky and now I have more than 3 birds, someone might say, oh, okay, well, I see this group here and I see this group here. So I see 4 and 3, and I know 4 and 3 is 7. That's how you might say it. So asking a lot, how many do you see and how do you know? And taking time to talk about that, because someone else might have seen that, or maybe you on the call here might have seen that differently. Maybe you saw this way, maybe you saw 4 this way and 3 this way. Our brains see things differently, and it's good to talk about. Like perception is a whole other, life skill and thing to think about when I look at something and you look at something and we see different things, and to talk about that. Like that's important, because we can both see 7, but our process of getting there can be very different. Someone could have even seen, 2 here and 2 here and another 3 there, and 2 and 2 and 3 equals 7. I love egg cartons. I do this a lot with my child as well, as you have it closed and you can open it quickly and close it. So subitizing also, you don't have to leave it open the whole time, but give them a chance to look at it, but not enough time to count 1 to 1. So to kind of open it, give them like 3 seconds to look at it and then close it and say, how many did you see? How did you see them? And in this situation, they might say, well, and you can open it afterward, of course. Maybe they saw 3, 1, and 4. Maybe they saw 4 and 4. So talking about what you see. And if they saw 3, 1, and 4, you can say something like, well, you know what? I actually grouped those all together and I just saw 4 and 4. And 4 and 4 is 8. Because the goal of this is to see the fewest, largest chunks, right? That's the least amount of steps my brain needs to do. On the right-hand side, you can see that there are rocks on the ground. And I actually place these purposely because I want the child to count a certain way. I actually want them to skip counting by 2s or 4. So instead of putting in the pile, I place them right here. And they might say, well, I see 2, 2, 2, 2, and 1. They might see, oh, well, I actually see 4 and 4. It kind of looks like a dice, but I just moved them together a bit. And 4 and 4 and 1 is 9. So just talking about these. And these are just called, it's just called subitizing, but it's really the beginning of adding, right? You're taking chunks and you're composing numbers. So in this here, I've actually have a document that you'll get as well of a bunch of different images where you can just talk about how many do you see and how do you know. And I've placed the rocks so that you can just have this conversation with them. But I place them very purposefully. I've even done it with tomatoes as well, where I put it in I put it looking like a 6 on a dice and 1 more. So what's 6 and 1? 6 and 1 is 7. So it's the beginning of adding. Here they might see, I'd put an egg there. This you might see 4 and 2, and 4 and 2 make 6, but I put them in the shape of the 6. So I have this whole document here, and I actually placed them again very purposefully for kids to see. This one here, I have 4 and 4, so it's working on doubles. This one's working on near doubles. So I have doubles plus 1, which is a concept. So again, this whole document you'll get, and you can just talk about these images with your child and just talking about how many do you see and how do you see them. Something else that you could do too is with board games as well, using dice. Again, I love dice and different variations of dice. So if you're playing a board game, say snakes and ladders, instead you could use 1 dice and say, okay, you're going to go the amount of times, not just by the roll of the dice, but we're going to double the number. So if you get a 4, can you visualize another 4 and how many dots would that be? So that's a way of doing a variation. You can play with 2 dice and adding them together. You can play with 2 dice and say, okay, the amount of places you're going to go is finding the difference between the 2. So if I roll a 4 and a 2, you actually are going to go only 2 steps, the difference between the 2 numbers here. Playing cards as well, they're subitizing. They have the different symbols on them. What you can do is actually cut off the corners, get a deck of cards and cut off the corners with the numeral, the number 8, and then flip them over. And they have to see if they can, you can play, you can kind of play who has more war. You can play memory matching games with them. You can play dominoes. So all of these different types of games that you have at home, you can play with dice, and this is all with subitizing. Christina Tundervolt, she's someone who's a really great resource, and she has a ton of subitizing cards on her website that are for free that you can download. Again, this will be on the PDF that I'll send you. And you can play memory matching games with these. Make math moments. They also have different bingo games that you can play and rolling of the dice where there's actually no numeral, but they actually have to look at the dots. And we're thinking about how are they seeing them? We want to move away from counting 1 to 1. That's the goal. That's the goal of what we're doing here. The next part here are the models that we're using to represent. So using cubes here, like we talked about, using 10 frames right here. Something I'm going to talk about is the bar model today. We've talked about the number path. We've talked about the number line a little bit too. The number path comes before the number line. And I'm also going to touch on something called the math rack or the rec and rec as well. So these are powerful visuals to show what's actually happening when we're adding numbers, because when we start subitizing larger amounts, that's what we're doing. We're composing numbers. So the next one is called hierarchical inclusion. And this just means that there's numbers nested in within numbers. So within the number 8, I have a 1 and a 7, a 2 and a 6, a 5 and a 3, a 4 and a 4. But within 8, there's also a 1, a 3, and a 4. I also have a 1, a 2, and another 1, and a 2, and a 2. So like in an 8, I have 8 ones. So we can really decompose these numbers into smaller chunks. And this is really, really important when we get to things like 8 plus 6, because and these are called relational rods that I have on the image here. These are another manipulative that I really, really love because they can build the numbers and see how many there are. Because when you get to things like 8 plus 6, which is always kind of a tricky one for kids to do, and they'll go 8, 9, 10, 11, 12, 13, 14. They can also see 8 plus 6 as 8 plus 2 plus 4. And if I can decompose these numbers, I can do 8 and 2 to make 10, and then just add 4 more, which is a much more efficient strategy than counting by ones. So the bar model is just a representation of visual to show equivalence here. And the concrete manipulatives are these right here, the relational rods. And kids love them. They love building with them. But representing equations with them is something that you can start doing as well. That I can see that 1 and 7 is 8, but it's also 1, 3, and 4 as well. And from there, you can start writing equations. Oh, okay, 1 and 7 equals 8, which, and then they can also do which equals 1 plus 3 plus 4, which equals, they can start thinking about what numbers are nested within each number. So it's not just combinations to 10, 6 and 4 and 5 and 5. We really want to know all the numbers that are nested within numbers, all the different combinations for every single number, not just 10. Sometimes I find we focus a lot on the number 10, which is absolutely important. But how many combinations can we get with the number 6? Again, using 10 frames is really important. Again, the magnetic 10 frames, I have those. And then representing an equation that goes with it. So here we're talking still about the number 8 and how it can decompose and what it's going to look like. We did the bar model before. This is a 10 frame. This is another a visual model that you can use to represent it. So here you can see that I have 5. Oops, I have 5 plus 3, not 5 plus 8. So here I have 5 plus 3. And in this one, I have 3 plus 3 plus 2. Okay, so there's another combination to 8. And this one I can see I have 2 plus 3 plus 1 plus 1 plus another 1. That's another combination of 8. And this last one here, I have 1 plus 1, and I'm not going to do all of them, but I have 8 ones. So you can see here all the different combinations that you're adding together. And this is just within the number 10. So this is just number 8. Imagine all the other numbers as well. Think of all those combinations of numbers. Instead of focusing on, can you count to 100? right? Like we want them to know all of this nitty gritty stuff about every single number within 10, within 20, before we even go there. Do we want them to know that there's numbers beyond? Absolutely. And is it awesome that they can count that high? Absolutely. Like that's great too, but that's not probably something I'm gonna start with, like really focus on. But it is something important that they need to know. Absolutely. But kind of looking like this. With these 10 frames, I would actually put it up and say, you know, what equation does this represent? And can they write that out? Can they see that? The progression for teaching addition, I always start with making 5 rather than starting with 10. So all the different combinations to 5, all the different combinations to 10. Then I move to doubles. And this is great with dice. You can do doubles because they can clearly see the dots on them. Go for your doubles. Then I always do near doubles, because if I know doubles, I can do doubles +1 or doubles -1, doubles +2, doubles -2. So it's kind of your benchmark. Knowing your doubles is incredibly important. Then I kind of do 10 plus anything, because if we can get to the number 10 and 10 plus 4, kids need to know that 10 plus anything is really easy to do in my head. 10 plus 5, 10 plus 6, 10 plus 7, even though 7 is not a friendly number, but if I add it to 10, ooh, that's really easy to do in my head. And then 0 plus anything. We don't want to forget about the 0. Sometimes we do, but it's kind of like the pattern that we see in the number 10. 0 plus anything is really easy for me to do as well. So those are the kinds of things that we want to focus on when we're teaching addition. So this is, again, it's called hierarchical inclusion, numbers nested within numbers. It's addition, the beginning of composing numbers. And this is called a math rack, also known as a reckon rec. It's very different from an abacus, where it has all the same color, because that works on place value. This one, it has red and white beads, and it's focusing on making 5 and making 10. There are 5 red beads on the top and 5 white. So there's 10 beads on the top and 5 red and 5 white on the bottom. I'm not going to go into detail about how to use this tonight, because that's the whole other workshop that I could spend an hour and a half talking about and what to do. And we will do that. But this is just another concrete manipulative. And I've had kids make their own too. And they love using it when they make it. They cut their own wood, they sand it, they glue it together, they put on all the beads, they put their name on it, and they want to come over and use it. So I will share another time how to use it, but you slide the beads over, just like in this picture right here, and you have an equation. So I have 8 on the top and I have 4 on the bottom. How many total is that? Okay. So that's like the very condensed version. We can go into it more on another time. Unitizing is the last counting principle. And this means that you can count larger groups of items by decomposing the group into smaller equal groups. So in this situation, and counting correspondence. So I can see this as a 2-to-1 correspondence. I have 2 boots, but it's actually 1 pair. I have 2 lighter boots, and that's 1 pair. So I have 6 boots there, but I have 3 pairs of boots. I have 3 groups of 2. See how this is the starting of multiplication a little bit? Like I have 1 group of 2, 2 groups of 2, 3 groups of 2. Same with mittens. Another way to do this is with loose parts, is to get muffin tins and place like 2 or 3 in. This is the beginning of skip counting as well. Having equal groups, 1 group of 2, 2 groups of 2, 3 groups of 2, 4 groups of 2. And that quantity is more. So the count of the group of objects and see them as individually, but they can also see it as a unit of 2. 1 unit with 2 individual items inside. So this is kind of the last one. You can also see this when we talked to this about a little bit, how many do you see and how do you know? But when you're baking or cooking, you can always put things in rows and columns. So they can see 1 row of 4, 2 rows of 3 rows of 4, 4 rows of 4, and 2 at the bottom. So just talking about how they see that. I see 1 row, or they can count columns all together. So it's the beginning of skip counting. You can do this as well if you go on a nature walk, say you have a collection of pine cones, for example. How are we going to count these efficiently? So you can start putting them in groups of 10. Okay, so I have 1 group of 10, 2 groups of 10, and I have 2 more. 10, 20, 21, 22. So this is, again, the beginning of unitizing, meaning this whole 1 group is worth 10. and I can just count by tens. That is much more efficient than counting one to one. This money comes into play in this. I have a dime, and in this dime, there are 10 pennies. So I can count one dime, but it's really 10 things nested inside of that. Like sometimes I think about how confusing for a child, right? And then if we have a five, a nickel, though it's actually bigger than a dime, but it's worth only 5 of those pennies. So I can count 10 cents by 10, 20, 30, 40, 50, and again, 5 cents. So this is our base 10 system that I can see 10 as a unit or simultaneously 10 ones. So that really gets into skip counting as well. If I'm doing any sort of skip counting, I highly recommend using a number line to show what it looks like. So taking those leaps and jumps on a number line, again, still talking about the number line, and using the bar model. We've talked about this a little bit, or those relational rods. I can clearly see here all of the groups of 2, and they all equal up. So it's a very powerful visual for skip counting to see how many 2s go in the number 20. From there as well, when we're talking about equal groups, we can see that you can actually make different combinations of equal groups as well. Not just 10 equal groups of 2. I can have 2 groups of 10, which looks very different, even though I have the same amount. 2 groups of 10 and 10 groups of 2, that's totally different, but I have the same amount. And 4 groups of 5 and 5 groups of 4. So you can see this is actually the beginning of multiplication. Even in kindergarten, people are like, oh, kindergartens don't multiply. And I was like, well, it's really important they understand unitizing, because that is the beginning of multiplication. And if they miss this anywhere, they're going to have a lot of trouble counting units of things. Again, so these are powerful models that we can create. You can buy magnetic number lines and bar models like this online. I also just draw them out of lot too. They're rectangles. They're very easy to draw and partition. So if you have 20, like you can have 2 groups of 10, and just starting to talk about how many different combinations can you make with that. The bar model is also very powerful. And instead of putting the answer all the time, you can leave things blank and say, you know, we have 20 items now, and doing it reverse. Instead of counting the items, say we have 20 items. How many would be in 4 equal groups? Like, let's place them all. Let's count them all out and put them in 4 equal groups, and let's see how many would be in each one. And starting to talk about division here as well. You can also use it for addition and subtraction, the bar model. So if I have 20 pine cones and I had 2 groups, I can see here spatially, how much do you think was in each group? 2 people got some. How many do you think each got? Well, maybe this person said, well, it's probably, you know, maybe, I don't know, maybe it's 18. I think this is 18 and I think this is 2. And again, they didn't say this one was 2 because that one is a lot larger. So they're using their spatial reasoning skills. So the bar model is a very powerful model, even for addition as well. So the progression of this is always using concrete manipulatives that you can actually physically touch. The second one is the visual and models, and that's what I'm talking about a lot today. And then the third one is the actual, 6 plus 7, 12 minus 7. So sometimes we jump way too early to that abstract model without doing a lot of work in the early on phase. So I'm just going to show you what this looks like. So now, okay, your child's starting to add numbers. They have 7 plus 9. A lot of kids, this is a tricky one for them to do. They're starting to count on their fingers, but these are some different strategies I'm going to talk about. So a child might do 7, plus 7. I'm going to redo that because that's not a very nice job. Try that again. So they might say, okay, you know what? I did 7 plus 7 because I know my doubles, and I know that in the number 9, there's a 7 and there's a 2. Remember, we're coming back to hierarchical inclusion. There's numbers nested within numbers. So I see 7 plus 7 and I see 2 more. So I did plus 7 and plus 2. That was my strategy. So here we're starting to talk about strategies. Another child might say, I used doubles too, but I did the doubles of 9. I did 9 plus 9. And then what I did was I subtracted 2. So I did 9 plus 9 minus 2. This is coming back to, remember, doubles plus 1 minus 1 plus 2 minus 2. These are where these strategies come out, and using a number line to make those jumps on there. And you'll have to annotate it for your child at the start, but the goal is for your child to be able to look at a number line and be able to do it themselves. They also might say, you know, I noticed 9 is close. It's 1 less than 10. Again, that language coming in. So I know it's 1 less than 10. So I could start at 7 and I could add 10 because that's easy to do in my head. And then I just take away 1 at the end. And so I still get to 16. So these are 3 different strategies of adding the numbers. Another what a child might do is getting to the number 10. Remember that how many to get to 10? I'm 3 away from 10. So I could get to the number 10. So I add 3. And if I know that there's a 3 and a 6 in the number 9, because we've done all of that work before about making those combinations, then I can just add 6 more. That's why it's so important to know this stuff and to take time to do it as well. Or if they know, they could say, I started at 9 and I added 1 more to get to 10. And then I added 6 more here to get to 16. So getting to a friendly number, I'm at 9, I'm 1 more to get to 10, and 10 plus anything is really easy for me to do. Again, coming back to the progression. So there's a reason why that's all happening there. They could also think as 7 plus 9. So I have 7 pine cones and 9 acorns, and I can actually take one of these. If I count them all together, if I take one of these and I just put it in this pile, I then have 6 and 10. And 6 plus 10 is a lot easier to do in my head because they know it doesn't matter which way I count them, I'll still get the same answer, and I can move them in groups. And that's really important that they understand that concept. And that was earlier on that we talked about it. And 10 plus 6 is a lot easier to do in my head. This is called compensation. Pam Harris calls it give and take too. I can take one and I can give it to the other and I'll still get the same answer. It's a very efficient strategy for kids to use. Again, using like a scale, like a balance scale like this with kids, with cubes, that's where that algebraic thinking comes in, and thinking about relational thinking, relationships between the numbers. So without computing, so without solving 9 plus 8, what do you think this number would be? And taking time to ask kids this. Don't solve it, just look at the numbers. What do you notice? And they might say, well, you just added 1 here. You just added 1. Okay, so what number do you think would be here? And it's actually you just have to take away 1 then. Oh, so 9 plus 8 is the same thing as 10 plus 7. So practicing these. This is from Pam Harris. This is on her site. Again, this will be in the PDF that you get. And she doesn't want you to compute. She wants you to think about relational thinking. And this builds higher order thinking skills for kids. This is the beginning of algebra. And again, why do we do this? Because decimals come later on and you can use these same strategies. If I have 2 and 6 tenths, well, I see 3 and 8 tenths. I can actually add 4. I can go over and I can get 6 and 6 tenths, and then I can come back 2 tenths to get 6 and 4 tenths. So I can use strategies. I don't have to stack them. I don't have to line the decimals up. I'm just thinking strategies. I'm looking at the numbers and thinking about what I could do. I could also take 2 tenths from here and I can give it over here. I could take 2 tenths from here to make that a whole number. So it would become 2 and 4 tenths plus 4. And that's a lot easier to do in my head, right? So we're taking some, giving and taking. We use these strategies with decimals, fractions, and with lower magnitudes of numbers. So building those strategies at a young age is really important. And Pam Harris, if you go on her Instagram, she has, you can download this guide for free, which I'll put the link in that PDF, but she has these strategies in there and she really talks about them and what they are. Because it's not that there's 100 strategies for everything. There's actually really only 5. And being able to know what those are, it doesn't mean that they have to know every single one, but are they using some of those strategies efficiently? Then we get into subtraction, 15 minus 9. So Again, looking at 15 and breaking apart the numbers. That's the hierarchical inclusion, numbers nested in within numbers. Well, I really want to get to that number 10 because I know 10 plus anything or 10, if I minus anything from 10, it's pretty easy to do in my head. So I can take away 5 and then I just have to take away 4 more. And I know that's 9. Or you can say, I know 9 is 1 less than 10. I can take away 10. So I could take away 10. Oops, I'm just going to redo that. I can look at 9 and say, okay, you know what? I'm actually going to take away 10, start at 15 and go all the way down to number 5, but that was too much. We took away too much and I'm just going to add 1 here. And I get to the number 6. My jumps are really great on this technology, but you can see how they're using strategies. They can also think of subtraction as addition, as adding up instead. So again, this is where the bar model comes in. The 15 is our whole. I know there's 9. How many more to make 15? So if I start at the number 9, how many more to get to 15? They might say, okay, well, 1 to get to 10, and then it's just 5 more. Oh, well, the difference between the numbers is 6. Oh, can you add even though it's a subtraction? Kids get really confused if they've never been taught or just opened up to that strategy, which is a very intuitive strategy for them to actually do. And that leads into, the difference between the numbers, the distance between both of them. So if I have this red dot here and here between 9 and 15, it's actually the same distance if I did 10 and 16. That distance is the same. It's the distance of 6. I just shifted it over. So that is actually the same thing as 16 minus 10 equals 6. And that's called constant difference. Again, these are really efficient strategies. And I know that there are a lot of them to kind of go through, but the reason why we do this is because when kids get to larger numbers, instead of stacking them like this, and taking all this time to carry over and borrow and teaching them all the strategies of how to do that, you can just think about the numbers and where are they on the number line? And, oh, well, 96 is close to 100. It's actually 4 away. And then it's just 1 more. The distance between both numbers, oops, this is 1,000, not 100. And it's 1,001. So they can see the answer is 5. That is much more efficient than start on the right side, go over. Oh, it's a 0. You got to go over again. Oh, it's another 0. You got to go next door and knock on the doors. Don't make any tricks and memorize steps for that. Talk about thinking about what the numbers are and where they are on the number line. Because I can really add up in this situation, even though it's a subtraction. I've done this question with kids so many times. It's always my go-to. And kids who've never been exposed to different strategies, 99% of the time, take all the steps to go through the whole thing. And when I show them, oh, the distance is just 5. They're like, what? Oh, yeah, that's right. I didn't even think about that. Because they're just thinking very tunnel vision. So again, number lines, bar models, you can get the stuff, you can get a few online, you can print them out. They're very easy to do, even just with your hand. But it's really great to introduce as well. And the subtraction, the strategies are there as well on Pam Harris's website. And I will talk more about them. And I will have workshops to come on to actually practice this, because I know I'm just telling you it and I'm showing it to you. It's a totally different thing for you to actually draw it out as your child is speaking. That's a whole other thing. And I've been doing this for a long time, but listening to a child's thinking and then making their thinking visual takes a lot of practice, like lots and lots and lots and lots. I've been doing this for, 10 years. So I will have workshops to come on how to practice that with your child, because numbers come up everywhere. The answer is always, it depends on what your child says, will depend on what your visual looks like. So there is actually no one resource or one book for your child. And I know sometimes that's hard to hear because we just want that because we need support. But I will be running things to help within that process to really build that number flexibility. And just
sorry, can I interrupt with a quick question? Someone was asking, how many concepts do you focus on in a lesson?
Um, if a number situation comes up and a child, if you have multiple children, or if this talking about one child, if your child says an efficient strategy, I would just talk about that one. If they are counting 1-to-1 or they're not thinking very efficiently, I would model one strategy to make it a little more efficient for them. And this isn't, okay, 1 week I'm going to teach this strategy. The next week I'm going to teach this one. The next week I'm going to teach this one. That's not really how it works because it depends on the numbers. I wouldn't get so hung up on them knowing the name of the strategy and making sure that they know all of them. I always tell people don't like test them on these strategies or anything. You can see if your child is thinking efficiently. And then when you see an opportunity to introduce another strategy because it's actually more efficient than what they're thinking, do it, but only do one at a time. Don't say, oh, okay, this is how you can solve the problem 8 different ways. If they're thinking efficiently, don't even show them anything else. But you can say, oh, you know what? This is actually how I did it. And then you can talk about it. But I would not show multiple strategies unless, like, I've had big groups of kids where I've had 5 different strategies thrown at me and I'll put all 5 up on the board, but I won't put anything up that hasn't been said. But I won't lie, I've like planted seeds in situation where I want certain numbers to come up because I want to talk about a certain situation. Especially when you're making change with money, a really efficient strategy is to count up making change. Kids always, a lot of the time, have trouble making change if they're trying to subtract in their head. And they have to do that mentally when they're, doing some sort of entrepreneurial project. So having them count up. So I will use numbers sometimes for a strategy to come out. And that actually weaves in pretty well here where we talk about a mental math strength. So doing mental math on a regular basis doesn't have to be every single day, but on a regular basis. Pam Harris has something, and Kathy Fosno and Sherry Parrish, they have something called a math string. So it's a series of equations. You see here, you start with 13 minus 3. And this one is removed to a friendly number. So she wants this strategy to come out in this math talk. So it's like direct teaching to your kid a little bit, right? What's 13 minus 3? And they might say, oh, it's 13. For the first, I'll just do the first one. You actually don't show them all. You only show one at a time, but all of them are there. So you would say, what is 13 minus 3? And they might say, oh, okay, well, it's 10. How did you know that? Well, that's easy. It's just, I know it's 10 because it's minus 3. Okay. So what would be 13 minus 5 then? And they might say, oh, okay, well, it's just 2 more, right? We already did minus 3 and it's actually just 2 more. If I minus 2 more, then I'm at the number 8. So I want to get to a friendly number. I'm removing to a friendly number and a little bit more. So you can see here, she purposely crafted these numbers for a strategy to come out. So these resources I find really helpful if you want to talk about a specific strategy. The next one would be, what is 17 minus 7? And they might say, well, that's 10. That's easy. I can do that in my head. And the next one is, well, what is 17 minus 8? And they might say, well, I know 17 minus 7. So 17 minus 8 is just 1 more. It's 9. So in this situation, you have a series of related equations because you want a certain strategy to come out. But I wouldn't do multiple strategies at once because that could be very confusing. Again, all of these resources will be in the PDF, and I will do a lot more about mental math and these strategies. But the one advice I can say is just listen to your child, think about what they're saying, and think about how you can make their thinking, the words that they said, a visual. And our goal, and using a number line or a bar model or 10 frames, those are really the ones your go-to. So that model will stay a lot the same, but the strategy that they say might look different each time. Or it might look very similar. And if they use the same strategy all the time, with different numbers, there's more efficient strategies, right? Like it just depends on the numbers. And that's important. We want kids to look at numbers and think about them and think about what would be the most efficient way, which is a life skill. So, and then if you want to push their thinking as the guide, model your thinking. Oh, well, I actually did this. Instead of removing by ones, I took a larger chunk to show them, I got to a friendly number because friendly number is 10. So just modeling that for them and they will pick up on that. Like they will, if they see the visual. You just saying that is actually not enough, in my opinion. They need to physically see the model repeated over time. And if you have a group of children, making sure that so-and-so can see the other person's strategy on the visual, because they might not understand it when they hear it abstractly like that. So thank you so much for listening. That was a lot of math talk. Are there any questions before we wrap up here?
I guess just something to add to the end. Erica had mentioned she's going to put a number line in her pocket to move around the farm.
Yes.
So I suggested a measuring tape because they have one at Home Depot with a little clip. It might be
Yes.
and so she enjoyed that tip. And I remembered IKEA. I've never taken many measuring
And
tapes.
laminated them. That's what I do. I was literally just about to say at IKEA, just they have the paper measuring tapes and I've laminated them, and they're great because they can kind of fold up and you pull them out and take a whiteboard marker and go along them. And I always carry a whiteboard with me wherever I go too. Just so that you can create a number line on your own. An open number line is when, I'm just going to show it here, is when I was just doing this. I just put the numbers on it, 0, and I put 25 here. And I don't need to put every single tick and every number in between. You can just, if it was say like 15 plus 7, I can just start at the number 15. I don't always have to start at 0. And then maybe they did plus 5 to get to 20, and then 2 more to get to 22. But I think I'm going to have something to practice annotating thinking, annotating meaning, making the visual, because I know sometimes that's the tricky part as well. So that's awesome. Thank you, Erica.
And
if you do anything, can you please take pictures or videos of that? Because I want to see you walking around with the whiteboard on the farm and all the opportunities and the numbers that come up on your farm, because there are so many. So that's awesome.
And because everyone's so eager for your resources, I have downloaded all the files for you. So, but it's great because then she can combine her resources and it'll all be there ready to go. So I will send that to you right away.
Awesome. Thank you, everyone. Thanks, Erica, for coming.
Yes, thank you, everyone. And we really appreciate Gillian's wisdom and knowledge. You are incredible. So we appreciate your passion for math.
Someone has to, right?
The entire next generation of humans
yes
does. So have a great night, everyone. Thank you so much for coming, and take care.